Hello everybody and welcome back to part 2 of Exam 1 content. In the previous video we covered all the material that would have been on quiz 1 and about half of the content that's on exam 1, but that video got too long, so we're going to finish it up here right now. So as far as percentages go, you might see percentages just in prescriptions in general, and they can relate three things to each other. They can relate weight to volume to volume, or weight to weight. Volume to volume is typically how many milliliters are in 100 milliliters. Weight to weight is usually how many grams is in 100 grams. And then the only one that's a little complex is weight to volume. It's how many grams are in 100 milliliters. And in the last video, I covered something similar with ratios, how it's always grams to milliliters, as opposed to like milligrams to milliliters or grams to liters. So just really remember that, because again, that can make your whole solving process, your final answer, off by 1,000 times, just depending if you don't use grams to milliliters. So as far as that goes, we did talk a little bit about ratios. They're typically used to express weak concentrations, and they can relate mass to volume as well. They can also be used to relate volume to volume. I think the only example we've seen so far is mass to volume, but there are also mass to mass and volume to volume, similar to percentages. However, it doesn't really change the solving method too much. For example, I don't know if benzalkonium chloride is a solid in a solid. I don't know. I'm assuming it's something in a liquid, but it could be grams, it could be a volume, but either way, your solving process is going to be the same. If you want to express this as a percent, all you have to do is we can put one, we'll just call it unit in the numerator, because again, we don't know if this is in grams or if it's in milliliters, but it doesn't really matter, over 2,000 milliliters of solution. If we solve that out, we get the number, let me put in my calculator, 0.0005 would be essentially what that ratio equates to. Now, what does that mean? Or how do we turn that to a percent? So something interesting about the percent symbol, you might have heard Dr. Hagner mention this already, but when we multiply something by 100%, we're essentially multiplying it by 1, because we multiply by 100, but then we have the percent symbol. And what this actually means is, what a percent is it actually means 1 over 100. It's like a variable, and that's what it means. It's like how pi is 3.14. This equals essentially divided by 100. So when we multiply by 100%, we're multiplying by 100 and then a variable that equals 1 over 100. So that's just 1. So that's why we're able to do it. So in order to get this into a percent, we can multiply 0.0005 by 100, and that'll get us an answer of 0.05%. And it's important we keep that percent in there, because remember, otherwise we would have just multiplied by 100. But since this symbol means divide by 100, we're good to go. And that'll be our final answer on how to express this benzalkonium chloride solution as a percent. Or it'd be 0.05, just to get in the habit of putting our leading zeros. So okay, that's a pretty simple example using a ratio. How can we do this when it's actually like a script that has to do with compounding? So right here, we have a prescription. It wants us to QS 60 grams, and we have these ingredients. And it wants to know how many grams of petrolatum we actually need. Because again, that's a quantity sufficient. It won't be 60 grams. It'll be the amount we add to get the final product to 60 grams. And we did talk about that in the last video, in case you need to go and review that again. So the easiest way to do this is to take 60 as our total solution, subtract 20 grams, because you can see we have 20 grams of lanolin. We have 40. Now what do we do here? We have 3 ingredients that are each 8%, and this means each individual one is 8%. This does not mean each one, or all 3 of them together are 8%. So we can actually take our 40 and subtract 60, because this is our total solution mass, and then this multiplied out by 8% 3 times. So 8% is equivalent to 0.08. A way you can show that is actually 8%, Remember that a percent is 1 over 100, so we're dividing 8 by 100. So that's 0.08, 0.08. And since there's 3 of them, we add those together. So 0.08 plus 0.08 plus 0.08. And let me plug that in my calculator really quick. Come out with this final answer of 25.6, and that's how many grams of petrolatum we need. So that's our final answer for this one. So you can see that the way we solved that was basically, since 60 is our total, taking 8% of 60 3 times for each of the 8% components, and then subtracting it from the 40, which the 40 was just from the 20 grams we already subtracted. That'll get us our total value. For this next one, how many grams of methylene blue are required to compound the following prescription? So this one's interesting. This is similar to a percent, right? We want this amount of the total solution, but what is that amount? So the way we can solve that, and it actually tells us grams here, so we do know this is a grams per volume, but that doesn't really change how we solve the problem. So what we can do is we can kind of do what we did above. We can take 1 over, instead of 2,000, as we did in the top problem, 20,000 for this problem, because that's the concentration, and that will equal 0.00005. Similarly, we can turn that into a percent by multiplying it by 100%. And now we're left with 0.005%. Now all we have to do is take 60 minus 60, because that's our total value, times 0.005%, which we technically didn't actually need to turn it into a percent here. I like looking at the percentages better, but since this is just going to be multiplied as 0.00005 anyways, it doesn't technically matter for this problem. But the reason we're subtracting that is because that is the quantity that, or actually, just kidding. Or am I kidding? No, so we're actually not subtracting from the 60 here, because we already know that 60 is a sufficient quantity. Instead, it's actually simpler. We're just taking our 60, because that's our total value, and we're finding what 0.005% of that is. So it's literally just this segment right here. So if we do 60 times 0.00005, we get 0.0003 grams. And that would be something that would be a lot easier to express in milligrams. It's just, since it wanted us to express it in grams for this problem, it's just how we have to express it. And you could use scientific notation, which we talked a little bit about last video, to make that a simpler value. For this problem, I think it's like within reason to just ignore it, because it's still a pretty small number, or a pretty, not small number, but number with not too many digits. So that's why I'm fine leaving it like that. But if you wanted to, you could always convert that into scientific notation, which I think would be 3 times 10 to the negative 4th. Okay, so now let's talk about specific gravity. And this is essentially the same concept as density, because all it is its weight or mass divided by volume. So this seems like a pretty simple concept, and it is for most problems. I picked out 2 somewhat difficult examples, just to hopefully show you how to work through more complicated problems. So let's get started on those. So basically, for this first problem, we want to know how many milliliters, so that's the final thing we're solving for. If we use an 88% solution of lactic acid, also assuming this solution has a specific gravity of 1.21, are required to make the following product. So where do we even begin on a problem like this? Well, at first, I like looking at the prescription to see what we have information-wise. And you can see that we know we have 5 grams of lactic acid. So that can be our starting point. We can find out, since this is a weight per weight solution, we can find out how many grams of total solution we need. And when I say total solution, I mean the 88% solution, in order to actually get 5 grams of lactic acid. So the way we can do that is we can model 88 grams of lactic acid over 100 grams, we'll just call it S for solution, equals 5 grams of lactic acid. Since this is our active ingredient, this is what we need to solve for, over X, because we don't know how much total solution we need. So what we can do is we need to isolate x. So we can multiply x through, and then we can divide by 88 and multiply by 100, because this will essentially allow us to isolate. It's just solving a proportion. My previous video, I mentioned that it's a lot easier to put x in the numerator. Again, it might not always look clean, and I wanted to, at least for this percent problem, not do that to show off kind of how to model a weight for weight solution. But if you model this with x in the numerator, you're a lot less likely to make a mistake. So I'd recommend doing that when you solve that, but just for the purposes of this problem, I wanted to show it with x in the denominator, just to hopefully make things make a little more sense. So what we have to do is we have to take 5, divide it by 88, then multiply it by 100. So we get that we need a total of 5.68 grams of solution in order to get our final product. But that's all well and good, but this solution doesn't have a specific gravity of 1, meaning we have one more step. And essentially what we can do is we can set up our equation. Specific gravity equals mass over volume. So we have our mass divided by an unknown quantity, an unknown volume. We know our specific gravity is 1.21. So again, just another proportion, we divide by 1.21 and multiply x over to this side. And what we get as our final answer is 5.68 divided by 1.21. We get that we need a total volume of 4.69 milliliters. Let me erase that, that's not super clean. 4.69 milliliters. So that's how you solve that. As you can see, it was 2 steps, but we did need to pull a lot of information from a lot of places. But the nice thing about specific gravity is as long as you use one proportion, because you pretty much know you're always going to need one, that mass, density, and volume relationship, you should at least know you're kind of on the right track. In this case, we actually needed 2, but that was just because of the nature of the problem. This next one I think is a little bit easier. We need to find the percent volume per volume of a solution if we have 225 grams of acetic acid, which happens to have a specific gravity of 1.045. We need to make 1.5 liters of solution. So this first step is actually kind of easy. We know that our denominator in our percent volume per volume is going to be 1.5 liters, which we do need to convert to milliliters, so that's 1500 milliliters. So that's already half the problem done right there. Next, we need to set up our specific gravity equation. So Sg equals mass over volume. And in this case, we're solving for volume, so we can actually rearrange this equation. I didn't show it rearranged this way last time, but this is essentially we're doing the same thing. It's volume equals mass over specific gravity, because we do have all the numbers for these things. So our mass is 225 grams for a specific gravity of 1.045, and this will equal our volume, which let me put that in my calculator really quick. 225 divided by 1.045. You get 215.3 milliliters. So now that we have that as our volume, we can simply do our volume per volume. So 215.3 over 1500. This gets us 0.1435. We need to multiply that by 100%, which will get us 14.35%. And that's our final answer for that problem. So again, that one was a little bit easier, in my opinion, because it helped that it was volume per volume. I find when it's mass per volume, it's probably the most complex those problems get. But if you understand how to do these, you should honestly be fine for any specific gravity problem you're given. So now let's introduce a new unit, drops. Now drops aren't standardized in the way that, something like milliliters are. It's not a specific set amount of volume. But for the purposes of this class, if you ever see drops in a problem, you can assume 20 drops per milliliter of water, unless the problem says otherwise, because there might be problems that will actually have you solve for drops. But that's just something you need to know. And you can solve them very easily with dimensional analysis. Let me do a problem really quick just to kind of show that. Did I put a drops problem on here? I might not have. Well, okay, if we see a problem with drops, I'll make sure to call it out and do that. What this first problem wants us to do is a physician orders clonazepam 0.05 milligram per kilogram per day, divided into 3 doses for a patient that weighs 60 kilograms. So how many milligrams of clonazepam should we have? And for this, I will actually hold off because I do want to teach ideal body weight first. If a problem doesn't ask you for ideal body weight, you don't necessarily need to use it unless like somebody has already stated you should use it, but it kind of varies. Most hospital settings will actually automatically calculate ideal body weight. Ideal body weight is typically used for patients whose body weight don't necessarily fall into like a standard deviation. For example, someone that's very tall or someone that weighs a lot or a little. Because at the end of the day, doses should be given based on number of targets, and weight can't always accurately depict that one-to-one. So instead we have this equation right here. It's a little different for females than for males. It's 50 kilograms for males, 45.5 kilograms for females, plus 2.3 kilograms per every inch of your height over 5 feet. And for example, if you're less than 5 feet tall, I actually don't know if you subtract it from ideal body weight. I think you might, but don't quote me on that. That might be a question for Dr. Hegner. I have never encountered a problem thus far where they give us a patient less than 5 feet, because in pharmacy school, at least in a lot of your main classes, will not focus on pediatrics, which are typically where you're going to be seeing those smaller patients. But something to note, I might actually ask him about that and maybe make a comment on this video if I find that out. But anyways, that shouldn't be something you have to worry about too much. So I can just really quickly show you how to solve that. So we have a man who is 6'2", who weighs 98 kilograms. What's his ideal body weight in kilograms? Now, since we only want ideal body weight, we actually don't need to worry about his actual body weight. There is another metric called adjusted body weight, which you would, but for this problem, we just need to focus on ideal. So we know that his ideal body weight is going to be 50 plus 2.3 times inches over 5 feet. Well, we know there's 12 inches in a foot. That'll get us to 6 feet. Plus 2 more is 14. So if we put all that into our calculator, 50 plus 2.3 times 14, we get that his ideal body weight is 82.2 kilograms. And this is what we could use for dosing. Also, another thing is if you receive height in a problem, then it probably wants you to do ideal body weight. But if you're just given a regular body weight, then you can't really solve for it. So you shouldn't really worry about it unless you see a height. In which case, assuming it's something you can ask and the problem doesn't specify it, I definitely would ask. There's no reason losing points, but yeah. So next thing is body surface area. This is a little less common. A couple things I want to call out with it. It's weight in kilograms. That's pretty standard for things like BMI and ideal body weight. It's actually height in centimeters though, which is a little strange because, for example, BMI will use meters in its equation, which I think you get BMI later in this course. If not, you'll definitely see it in other courses. That's actually just weight in kilograms over height in meters squared. It's more for your reference. But yeah, just so you know. So let's really quick do a problem relating to that. So we have a patient that is 6 feet tall and weighs 212 pounds. The recommended dose for this drug is 60 milligrams per meter squared dose. How many milligrams should this patient receive? So what we can do is if you remember from our previous video, we know that 212 pounds times 2.2 pounds per kilogram, we can get their weight, which is 96.4 kilograms. Their height in centimeter is a little more tedious. We know there's 12 inches in a foot, meaning there's 72 inches in 6 feet. And then this is inches. We know that 1 inch is 2.54 centimeters. So really quickly, I can put that in my calculator, times 2.54. We know their height in centimeters is 183. So now we can use this equation 96.4 times 183 over 3600 0.4 divided by 3600. Then once you've done all that math, you take the square root of it. And in this case, I got a body surface area of 2.2. So that's their body surface area in meters squared. But what we need to do now is we need to take that original 60 milligrams. So 60 times 2.2 gets us 133 milligrams per dose. So again, the complex part of that problem really wasn't the dose itself, but it was just getting that body surface area, especially because it does have those centimeters in the problem, and almost all heights, at least that we take in the United States, are going to be in feet and inches. So that's probably the longest part. The same with the weight, we needed to convert it. So a lot of conversions, but the equation itself isn't too hard as long as you have a calculator that can do square roots, which I would highly recommend getting for this class. I don't think you're allowed to use graphing calculators, but looks like in my hand I have a TI-30, so I'd recommend getting one of those. I feel like that's the standard non-graphing calculator that you can find for probably like 15, 20 bucks. So now let's actually move back to that starting problem. Oh, and one more thing is you do need to memorize these equations. You're probably only ever going to get like 1 or 2 problems on these, but not knowing the equation literally makes it impossible to do the problem. So definitely make sure you have it just so you don't miss easy points. Let's go back to this one now that we're doing calculating specific doses. So this physician orders 0.05 milligram per kilogram divided into 3 doses for a patient that weighs 60 kilograms. How many milligrams should the patient receive per dose? Okay, so we know that we want our final answer to be in milligrams per dose. So something we can do, and to set ourselves up really well, is start with either milligrams in the numerator or doses in the denominator. I'll start with milligrams in the numerator. So we have 0.05 milligrams per kilogram. We can then do 60 kilograms because that's the patient's weight. Then we can actually just divide by 3 doses. Just put a 1 over this, and I'll, for the sake of it, put a 1 under that. And with that, we should just be able to multiply through, and this should give us our answer, how many milligrams they receive per dose. So 0.05 times 60. And if we stopped right here, this would be 3 milligrams. That's how many they should receive per day. But since we want to know how many they should receive per dose, and we know they get 3 equal doses in a day, 3 divided by 3 is just 1. So their dose is 1 milligram. Problem works out very nicely. We'll jump back down to number 3 now. A hospital pharmacist, as a hospital pharmacist, you were asked to determine the clindamycin phosphate for a 3-day-year-old neonate weighing 3 pounds 7 ounces. So already you can see we're probably going to have to convert either ounces to pounds, which there are 16 ounces in a pound, so that would be like 7/16 of a pound. I don't really want to do that, so we'll probably convert all this to grams. And as you can see, that looks like the right thing because in the literature we want 20 milligrams per kilogram per day every 6 hours. And that's evenly. So it looks like ideally that's going to be 4 doses a day, because if it's 24-hour day, 6-hour dosing regimen, then we get 4 doses. So how many milligrams will the neonate receive per dose? So we're actually going to divide this by, I'm going to make our lives a little easier to start with. Since we know they have 4 doses daily, I'm going to divide this 20 by 4. That it's 5 milligram per kilogram times dose. Now the hard part is just getting their weight in kilogram. So what I'm going to do is I'm going to, since there's 16 ounces in a pound, we have, with our 3 pounds, it's 48 ounces plus 7 ounces, 55. Then if you remember, there's 30 grams in an ounce, so times 30. 55 times 30 we get 1650 grams. There's 1,000 grams in a kilogram. So we divide this by 1,000, so we get that their weight is 1.65 kilograms. So now we can just multiply that through 1.65 kg, and that equals 8.25 milligrams per dose. So again, that problem wasn't too complicated. The two things that we needed to be able to identify, though, were that since the dosing occurred 4 times a day, and wanted to know the weight per each dose, we needed to divide by that 4 when I divided that 20 by 4 to get 5. We also needed to somehow get the pounds and ounces into kilograms. Alternatively, we could have done the pound way, converting the 7/16 of a pound plus 3, and then that times 2, or that divided by 2.2 to get our kilograms. It's not really a right or wrong way to do that. This is just the way I preferred, but whatever way is easiest for you is almost always the way you should pick. So our final problem on this page, clindamycin phosphate again, it is available as in a 600 milligram per 50 milliliter solution. How many milliliters do we need? So this is just a proportion problem. And we can see the increments on this are 0.01, so we know we need to round to that. Since we know that it's 8.25 milligrams, but we don't know the volume, but we do know it comes in volumes of 600 milligrams per 50 milliliters. What we can do is multiply this through. Remember, multiply your x, divide by 600, multiply by 50. So let me do that really quick. Times 50 divided by 600. And we can see that the answer I got in my calculator is 0.6875 milliliters, but since we need to round to that 0.01 increment, we can just round this up to 0.69 milliliters. And also I would probably round to that anyways, just because the 100th place is a lot nicer. And with something like clindamycin, the dosing doesn't need to be that specific. Like, this isn't a chemotherapy medication, so it's not, you know, an extra 0.0025 milligrams isn't going to hurt. So let's finally take a look at some problems that you might see on your final. Let's just work through them. Or not on your final, on exam 1, but you also could see these on the final since they're cumulative, so definitely learn them now while you can. So Sudafed prescription, 45 milligrams of pseudoephedrine per tablespoonful. How many milligrams will the patient receive daily if the patient takes it every 4 hours? So a lot to unpack here. So they're taking 1 teaspoon every 4 hours, I believe. Well, we need to look at the instructions. So 1 teaspoon every 4 to 6 hours. In this case, it tells us to use 4 hours, so we're going to go off that. And in our final answer, we want how many milligrams will the patient receive daily? And since daily, we could technically write this with daily in the denominator. We don't have to, but it's really good to set up our time this way, essentially. So the way I want to start setting this up is we know there are, actually no, we'll do it the long way, because I've been setting these up ideally since we've started, but I think it'll be beneficial to maybe show both ways. So we know that there's 45 milligrams per tablespoonful. Or I guess even this way we are setting it up in such a way where milligrams are in the numerator still. So it's kind of like I've been doing it all along, putting the units correctly. I just wanted to go based off time, but that's not as necessary. So 45 milligrams per tablespoon. However, if you notice on their prescription, they actually call for a teaspoonful for each of their doses. So how many teaspoons are in a tablespoon? Well, we know that 1 tablespoon has 3 teaspoons. From there, we know that they are going to be taking this essentially 6 times daily, because 24 divided by 4 is 6. So this times 6 times daily. And with that, we can just solve through. So 45 divided by 3 times 6 is they're going to get 90 milligrams of Sudafed a day. Let me show you where the 6 came from. So it's just 24 divided by 4-hour dosing. That's where I pulled that out of, and since they're doing that 6 times a day, I kind of just shortcutted that step, but just in case that wasn't clear, that's where I got that number from. So not too hard of a problem right there. Just, I think the hardest part was kind of knowing your tablespoon, teaspoon conversions. So definitely be like aware of those. Again, that conversion chart we talked about in the last video is super essential to memorize. At least some of the bigger conversions. For this next one, the recommended dose of tobramycin is 4 milligram per kilogram per day, divided into 2 equal doses. So that's important. Every 12 hours, that can be assumed from 2 equal doses usually. How many milligrams of tobramycin should be given every 12 hours? So basically, once every dose to an infant weighing 6 pounds 4 ounces. So this is another one. Since we know it's 4 milligrams per kilogram per day, similar to how on the problem on the previous page, we knew it was 20 milligrams divided by 4 doses. We're just going to go ahead and divide this one right away. So we know that it's 2 milligrams per kilogram per dose. And again, that's just 4 divided by 2 is how we got there because of the 2 equal doses. So now it's just doing the weight similar to we did last problem. Let's this time, just since 4 ounces divides a lot easier into a pound, we'll solve it this way. So we know that 1 kilogram is 2.2 pounds. And we know that 4 over 16, so 4 ounces over 16 ounces at a pound equals 0.25. So times 6.25 pounds. So we'll take 2 divided by 2.2 times 6.25. Then we get 5.68 milligrams. That's how many milligrams are in a dose of tobramycin. Again, you should really be writing out the drugs after each time, but I'm not, just to save space and time. For this next one, what percent concentration of weight to volume glycerin in the prescription above? Specific gravity is 1.25. So another specific gravity. It looks like we have 2.5 milliliters of glycerin. And in this solution, we essentially just need to, it's the final volume. Sorry, I'm trying to read this on my computer screen. It's very small. Oh, 2 ounces. Okay. So this one we need to, in this case, it's talking about fluid ounces. If you remember, our conversion from ounces to milliliters is that 1 fluid ounce has 30 milliliters. So what we can do is 2 fluid ounces then would equal 60 milliliters. So this is our total. This is what we're working with here. This will be our volume in the denominator. We have to set up our specific gravity equation. So Sg equals grams over milliliters. And we do have our volume in this case. So in this time, we actually need to rearrange the equation. Sg equals Sg times milliliters equals grams. We have 2.5 milliliters times 1.25 specific gravity equals grams. Let me put that in my calculator really quick. 2.5 times 1.25. We get 3.125 grams. We then will divide this by our 60 milliliters. This gets us 0.052. If we multiply that by 100%, because this does want a percent solution, we get 5.2% glycerin. Nice. Okay. So final problem, to wrap all this up, is we have this syrup which contains 80 milligrams of theophylline per tablespoonful. How many milligrams of theophylline will a patient have received after 3 days of therapy? So this one it's essential to again read the prescription. Realistically, to how you might see these in community pharmacies, a lot of the handwriting on these is very bad. So that in itself is part of the problem. This one isn't as bad, but on your exam, definitely, if you can't read cursive, like embarrassingly enough, I can't, at least not very easily. Definitely practice that because you will get some prescriptions that may be in cursive or really scribbly font. and it's just something you need to practice, unfortunately. But anyways, in this case, you take 1 teaspoonful by mouth 3 times daily. Okay, so what we can do is we know how many milligrams they want to receive, so we have 80 milligrams per tablespoon, TBSP. We know that 1 tablespoon is 3 teaspoons. We know that there's 3 teaspoons per day, and we know that this takes place over 3 days. So a really simple dimensional analysis problem if you know how to set it up. So all it is 80 divided by 3 times 3 times 3 again. And we get our final answer of 240 milligrams of theophylline. And with that, thank you so much for watching, and good luck on your quiz and exam.